Hello everybody, welcome back. Today we're going to take a look at the eigenvalue problem and linear algebra and how we can apply that to a practical problem. Okay, so what we have here is a system of masses and springs, and we're supposed to find the characteristic frequencies and the characteristic modes of vibration. So this is 5k is the spring constant for this spring. The masses are equal. And then these each have a spring constant of 2k. And so we can see that this x here is a measure of how much this first spring is being stretched. And this y here is a measure of how much this is being compressed. And then the difference between them, you can see that's going to be how much this middle spring is compressed. Additionally, we have this here. This is the potential energy stored in a spring. When it's displaced this much x amount from equilibrium with a spring constant k, it's not the same as these k's. We'll have to substitute in the proper values. And then this here, which is basically a rephrasement of Newton's second law, but applicable to oscillations. And we'll be using both of these. Okay, so the first thing we're going to do is we're going to write up a expression for the total potential energy stored in the system. So in order to do that, we just have to add up the amount of potential energy stored in each spring. So V equals 1/2. The spring constant is 5k in this situation, and the distance it's being displaced is x. So that'll be x squared. And then for the second spring, the 1/2 and the 2 cancel out. So this is going to be k. Remember what we talked about how it's being displaced. Its displacement is the difference between the two. And since we're squaring it, it doesn't really matter whether we're compressing or stretching the spring. It stores the same amount of energy either way. And then the last spring here. Okay. So I'm going to go ahead and rewrite this. So in here, this is going to FOIL out to be a x squared plus y squared, and there's going to be a minus 2xy. So rewriting this, we can see some of these are going to combine. So 7 halves kx squared minus 2kxy plus 2ky squared. Okay. Now for our equations of motion for this point x and this point y, we're going to start by writing the left-hand side of the equation out like this. And then we have to take the partial derivative of this expression with respect to x. This term is going to be a constant, so it drops out, and we're going to have 7kx minus 2ky. And we can rewrite this as once we actually take the proper negative, we can rewrite this as x times square root, my bad, m omega squared over k equals, and then since we took out the negative sign from there, we're going to have to take it out on this side too. 7x minus 2y. And we can do the same with our y here. And when we take the negative partial derivative of this with respect to y, this term drops out because it's the constant, and then we'll get 2kx minus 4ky. Once again, we can rewrite this as y times m omega squared over k equals negative 2x plus 4y. For simplicity's sake, we're going to call this lambda for now. It'll make things a little simpler. So we can set up a matrix for this equation now. And the matrix looks like 7, negative 2, negative 2, 4, x, y, and then this equals lambda x, y. So this is an eigenvalue problem. We want to find out what this value is, and we also want to find out what type of x and y actually satisfy this equation. So to work through it like we do any other eigenvalue problem, you can see that we can bring this over to this side and combine it with the x, and we would have a 0 on this side of the equation, and we would have a 7 minus what we've decided to call our lambda on this side, and then the 2y would stay the same. And similarly down here, we could move this over, the negative 2x would stay the same, but if we want a 0 on this side of the equation, this would be 4 minus our lambda times y. And solving the determinant gives us lambda squared. So then we have a minus 4 and a minus 7. So that means minus 11 lambda. Then we multiply these two together, 28. And we subtract 4 from the 28. So this factors out to give us lambdas that are equal to 3 and 8. So using this, we can now find out what our characteristic frequencies are. And I'll write this up here. If we rewrite the whole equation, our characteristic frequency 1, since since we have lambda equals that, we have to flip everything around and then take the square root. So our first characteristic frequency is 8k, the square root of 8k over m. And then our second one is the square root of 3k over m. Now this is great, but we still need a little bit more. We need to figure out what the characteristic modes of vibration. So in order to do this, we need to figure out which, we have our lambda now, but now we need to figure out what x's and y's will actually have this equation hold true. So we can do that by rewriting our equations once again. We can rewrite it from this step this time and substitute in for our lambdas. So that would be if we substitute in for 3. Then we have 4x minus 2y equals 0. And it's 0 on the side of the equation because remember in these equations, which we know hold, we move these over. So we're just, following from our previous work. And then minus 2x, 4 minus 3, plus y. You can actually see that these are the same equation, just that, they're multiplied by -2. So solving this, we get that 2x equals y. And so yeah, if our x is twice what our y is, which remember are these distances here, then our lambda is 3, and we have our characteristic frequency when that's the case right here. So actually we actually solved these in the other order that we did the other one. So we'll say the mode of vibration, which I'll write as a vector, but it's 2, is 2x for 1y. And this is technically multiplied by any number that you want. It's not it's 2 to 1 as a ratio, not as a absolute. And then with our other eigenvalue, we can find our other eigenvector. So 7 minus 8 is -1. Then our -2y stays the same here. Our -2x stays the same. Then we have 4 minus 8, which is -4. Once again, these equations are the same, essentially. They're equivalent. They're not necessarily the same, but they're equivalent. So when we solve it this way, we get x equals -2y. And so any vector or any x and y that hold to this equation have an eigenvalue of 8 and our characteristic frequency number 1. Okay, and applying this to this problem here, what exactly does this mean? So we have our one mass here, our other mass here. Well, here, I'll draw a little better there. Okay, so this means that when our frequency is this here, and remember that the top one is x and the bottom one is y, if this goes over, this amount, this other one is going over twice as much in the opposite direction. And this is when the frequency is square root of 8. Wow. Let me bring this to a place that you can read. There. So this is for our first mode. So when our frequency is 8k, or square root of 8k over m, then this one is oscillating back and forth, and at the same moment, this is twice as much in the opposite direction. And then in our second mode, we have our masses, and when this one goes over a certain amount, this one goes the same, but only half as much. When our frequency is at square root of 3k over m. Now it may seem like this whole situation is kind of contrived. How often do you have 3 springs and 2 masses in between them? Well, probably a lot more often than you think, considering that every metal and ductile material acts at least a little bit like a spring, including like bridges and such. So this situation might not be as contrived as you might think. There is another way to solve this problem that is quite interesting. Okay, here we have it. This is a method that I developed myself. I didn't read about it from anywhere else. But every eigenvalue problem of this form, where you have a matrix. Let's see, where you have a matrix of A, C, C, B, where A and C are not equal, or A and B are not equal, my bad. This actually is a hyperbola problem. So as we can see here, I have a hyperbola here plotted. And it's a special hyperbola where the intersections with the x-axis, or the y-axis, are they're the A and B in your matrix. The foci for the hyperbola are also similarly related. If you go from the middle of the hyperbola, you take one length to get to the intersection. You take square root of 2 lengths from the middle to get to the focus, or yeah, to get to each focus. It makes it very nice and symmetrical. And then our vertical line here is our C value. So we can see here, we get the same eigenvalues of 8 and 3 in the second coordinate of these intersection points. And it also tells you your eigenvectors, believe it or not. This vector here is your vector with respect to this eigenvalue, and this vector here is with respect to this eigenvalue up here. You could solve these complex problems with a compass, a straight edge, and a string that you can cut to a certain length, which is remarkable. So these eigenvalues and eigenvectors are the same. You can multiply them by any constant to get them into a form you want. Like for this one, we would multiply it by a -1, and for this one, we would multiply it by 1/2. But yeah, this graphical method or geometrical method has a surprising result also in the fact that if these vectors are always 90 degrees apart. And this follows from what we've learned about linear algebra and stuff in this class. These vectors are always orthogonal, and thus, if you ever want to take a line parallel to an axis of symmetry of a hyperbola, you can get yourself a free 90-degree angle by going from one intersection to the axis of symmetry and to the other one. If you have any questions, please feel free to put them in the comments below. And thank you so much for watching.